practical application of the 50% load diversity referenced in Table B 310.11 can be demonstrated with a commercial building scenario. Consider a commercial building with the following electrical loads: lighting at 60,000 watts, heating, ventilation and air conditioning at 40,000 watts, and equipment at 30,000 watts. The total connected load is 60,000 plus 40,000 plus 30,000, equaling 130,000 watts. According to Table B 310.11, the load diversity factor is 50% for general lighting and receptacle loads, and 100% for other loads. For lighting, the connected lighting load is 60,000 watts. The load diversity factor is 50%. The maximum demand diversity adjusted is 60,000 times 0.5, equaling 30,000 watts. For heating, ventilation and air conditioning and equipment, the connected heating, ventilation and air conditioning and equipment load is 40,000 plus 30,000, equaling 70,000 watts. The load diversity factor is 100%. The maximum demand diversity adjusted is 70,000 times 1.0, equaling 70,000 watts. Overall maximum demand is calculated as follows: lighting maximum demand is 30,000 watts. Heating, ventilation and air conditioning and equipment maximum demand is 70,000 watts. Total maximum demand load diversity adjusted is 30,000 plus 70,000, equaling 100,000 watts. By applying the load diversity factor, the calculated maximum demand is reduced from 130,000 watts to 100,000 watts. This has several practical implications. Firstly, smaller service entrance. The building can connect to a smaller electrical service entrance, resulting in cost savings. Secondly, reduced breaker size. In the main electrical panel can be equipped with smaller breakers, which are less expensive and easier to install. Thirdly, optimized wire sizing. The electrical wiring can be sized for the reduced maximum demand, resulting in material and installation cost savings. Fourthly, improved energy efficiency. Accurately accounting for load diversity helps ensure that the building's electrical system is not oversized, which can lead to increased energy consumption. Load diversity is a concept used in electrical engineering to account for the fact that not all electrical loads in a building or system will operate at their maximum demand simultaneously. This allows for a more efficient and cost-effective design of the electrical system. The load diversity factor is a ratio that represents the expected maximum demand of a group of loads compared to the sum of their individual maximum demands. A load diversity factor of 1.0 means that all loads are expected to operate at their maximum demand simultaneously, while a load diversity factor less than 1.0 indicates that the maximum demand of a group of loads is less than the sum of their individual maximum demands. Table B 310.11 in the National Electrical Code, or NEC, provides load diversity factors for various types of electrical loads. These factors are based on statistical data and engineering judgment and are intended to provide a reasonable estimate of the expected maximum demand for different types of occupancies and loads. In the example provided, the load diversity factor for general lighting and receptacle loads is 50%, while the load diversity factor for heating, ventilation and air conditioning and equipment loads is 100%. This means that the expected maximum demand for the lighting loads is 50% of their total connected load, while the expected maximum demand for the heating, ventilation and air conditioning and equipment loads is 100% of their total connected load. By applying these load diversity factors, the calculated maximum demand for the building is reduced from 130,000 watts to 100,000 watts. This reduction in maximum demand has several practical implications. A smaller service entrance can be used, which results in cost savings on the electrical service equipment and installation. Smaller breakers can be used in the main electrical panel, which are less expensive and easier to install. The electrical wiring can be sized for the reduced maximum demand, which results in material and installation cost savings. Accurately accounting for load diversity helps ensure that the building's electrical system is not oversized, which can lead to increased energy consumption. An oversized electrical system can result in high energy losses due to increased conductor resistance and transformer core losses. Therefore, It is important to carefully consider load diversity when designing an electrical system to ensure that it is both efficient and cost-effective. In addition to the benefits mentioned above, accurately accounting for load diversity can also improve the reliability of the electrical system. By reducing the maximum demand in the system, the risk of overloading and overheating components is reduced. This can help to extend the life of the electrical equipment and reduce the likelihood of failures. It is important to note that load diversity factors are not always applicable. In some cases, the actual maximum demand of a group of loads may be higher than the value calculated using the load diversity factors in Table B 310.11. This can occur when the loads are operated in a way that is different from what was assumed when the load diversity factors were developed. For example, if a building is used for a purpose that is different from what was originally intended, the load diversity factors may not be applicable. In these cases, it is important to perform a more detailed load analysis to determine the actual maximum demand of the system. A load analysis typically involves measuring the actual current and voltage of the loads over a period of time. This data can then be used to calculate the actual maximum demand of the system. The results of the load analysis can be used to adjust the size of the electrical service, breakers, and wiring to ensure that the system is adequately sized for the actual load. In some cases, it may be necessary to install additional electrical capacity to accommodate the increased load. It is also important to consider the impact of future load growth when designing an electrical system. The electrical system should be sized to accommodate the expected future load growth, as well as the current load. This can be done by adding additional capacity to the electrical service, breakers, and wiring. It is also important to consider the impact of new technologies on the electrical system. New technologies, such as electric vehicles and solar panels, can have a significant impact on the electrical load. The electrical system should be designed to accommodate these new technologies. In summary, load diversity is a valuable tool for designing efficient and cost-effective electrical systems. By accurately accounting for load diversity, it is possible to reduce the size of the electrical service, breakers, and wiring, which can result in significant cost savings. It is important to note that load diversity factors are not always applicable and that a more detailed load analysis may be necessary in some cases. It is also important to consider the impact of future load growth and new technologies on the electrical system. Here are some additional considerations regarding load diversity. Firstly, the type of occupancy of the building. Different types of occupancies have different load profiles. For example, a hospital will have a different load profile than an office building. The load diversity factors in Table B 310.11 are based on the type of occupancy. Secondly, the size of the building. Larger buildings tend to have lower load diversity factors than smaller buildings. This is because larger buildings have a greater mix of loads, which tends to smooth out the overall demand. Thirdly, the climate. Buildings in hot climates will have higher cooling loads than buildings in cold climates. This will affect the load diversity factor for the cooling equipment. Fourthly, the time of day. The electrical load on a building will vary throughout the day. The load diversity factor will be different for different times of day. Fifthly, the day of the week. The electrical load on a building will vary throughout the week. The load diversity factor will be different for different days of the week. Sixthly, the season of the year. The electrical load on a building will vary throughout the year. The load diversity factor will be different for different seasons of the year. Seventhly, the type of equipment used in the building. Different types of equipment have different load profiles. For example, a data center will have a different load profile than a retail store. The load diversity factors in Table B 310.11 are based on the type of equipment. Eighthly, the control system used in the building. The control system can be used to manage the electrical load in the building. A well-designed control system can reduce the maximum demand and improve the load diversity factor. Ninthly, the maintenance practices used in the building. Proper maintenance can help to ensure that the electrical equipment is operating efficiently. This can reduce the maximum demand and improve the load diversity factor. Tenthly, the age of the building. Older buildings tend to have higher load diversity factors than newer buildings. This is because older buildings have a greater mix of loads and the equipment is often less efficient. Considering these factors will help you to accurately determine the load diversity factor for a building and design an efficient and cost-effective electrical system. It's also important to understand demand factors, which are related but not the same as diversity factors. A demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system or the part of the system under consideration. It's essentially the maximum amount of power the system is expected to draw at any given time compared to the total power that could be drawn if everything was running at full capacity simultaneously. The demand factor is always less than or equal to 1.0. A demand factor of 1.0 means that the system is expected to operate at its full connected load at some point, while a demand factor less than 1.0 indicates that the maximum demand is less than the total connected load. The demand factor is used to determine the required capacity of the electrical system, including the size of the service entrance, feeders, and overcurrent protection devices. In the example given, the total connected load is 130,000 watts. But the calculated maximum demand using the diversity factors is 100,000 watts. The demand factor for the entire building would be 100,000 watts divided by 130,000 watts, or approximately 0.77. This means that the electrical system only needs to be sized to handle about 77% of the total connected load. It's important to note that demand factors can vary depending on the type of load, the occupancy of the building, and other factors. The NEC provides demand factors for various types of loads and different occupancies, but it's also possible to use engineering judgment and historical data to determine more accurate demand factors for specific applications. Here are some additional points to consider about demand factors. Firstly, demand factors are typically applied to individual loads or groups of similar loads, while diversity factors are applied to the entire electrical system. Secondly, demand factors are used to determine the required capacity of the electrical system, while diversity factors are used to account for the fact that not all loads will operate at their maximum demand simultaneously. Thirdly, demand factors are typically based on historical data or engineering judgment, while diversity factors are based on statistical data and industry standards. Fourthly, demand factors can be affected by changes in the way the building is used or operated, while diversity factors are generally more stable. Fifthly, demand factors should be reviewed periodically to ensure that they are still accurate, while diversity factors typically do not need to be reviewed as often. In summary, both demand factors and diversity factors are important considerations in electrical system design. Demand factors are used to determine the required capacity of the system, while diversity factors are used to account for the fact that not all loads will operate at their maximum demand simultaneously. By carefully considering both demand factors and diversity factors, it's possible to design an electrical system that is both efficient and cost-effective. Applying diversity factors and demand factors correctly requires a thorough understanding of the building's load characteristics and operating patterns. Electrical engineers and designers use these factors along with other considerations to create safe, reliable, and efficient electrical systems. Also, the NEC provides tables and guidelines for determining appropriate demand and diversity factors for various types of occupancies and loads. These tables are based on years of experience and statistical data, and they provide a starting point for electrical system design. However, it's important to remember that these tables are just guidelines, and it may be necessary to adjust the factors based on the specific characteristics of the building and its loads. In addition to the NEC, other resources are available to help electrical engineers and designers determine appropriate demand and diversity factors. These resources include industry standards, engineering textbooks, and software tools. It's also possible to consult with experienced electrical engineers who have worked on similar projects. By using all of these resources, it's possible to develop accurate and reliable demand and diversity factors for any type of electrical system.